So, in the last lecture we were looking at the use of correlations in balance equations. We first looked at correlations for low Peclet number, where the Nusselt or the Sherwood number was a constant, and those the Nusselt number is equal to 2 or Sherwood number was equal to 2 was substituted into a balance equation for the energy for the temperature of a particle, for example, or for a dissolving particle under conditions of low Peclet number. Okay. And we had calculated the rate of energy transport or the rate of dissolution under the condition that the time scale for the temperature variation or the diameter variation is much greater than the diffusion time. Low Peclet number limit, diffusion time is length square divided by the diffusivity. Okay. So long as that diffusion time is much smaller than the time for variation of temperature, then the time taken to establish the steady state, which is the diffusion time, is much smaller than the time scale for variation, and therefore we can assume that the temperature field around the sphere is at steady state, and use the correlation, that is Nusselt number is equal to 2 or Sherwood number is equal to 2, for example. And we had solved some problems for energy transfer from a sphere. We had calculated the ratio of the characteristic time and the diffusion time, as well as for the sublimation of a camphor particle. Okay, how long does it take? In the case of natural convection, the length scale for diffusion is much smaller, because any mass or energy diffusing from the surface gets rapidly swept downstream by the strong convection. Therefore, the disturbance due to the conduction, the diffusion from the surface is restricted to a thin region close to the surface, and therefore the length scale is much smaller than the characteristic dimension by a factor p power minus 1/3 for rigid surfaces, p power minus half for mobile surfaces where you have a zero stress condition, p power minus half into h by l power minus half for films, minus 1/3 into d by l power minus 1/3 for pipes, where d is the diameter and l is the length. And this has to be used in this expression for the diffusion time, where LD is the diffusion length, LD square by alpha, because diffusion length is much smaller than the characteristic time, the characteristic length. The time is much smaller than the time for diffusion over the length LC. And we had used this for natural convection from a sphere for two different problems. One is the heat transfer and the other is the dissolution problem. Okay. And so, in the case of the dissolution, you have a particle that is moving with some velocity relative to the fluid. Okay. And then we were looking at natural convection, dependence on Grashof number. Natural convection, because when you have a heated object in the ambient fluid, the fluid close to the object is at a higher temperature compared to the ambient fluid. It has a lower density, and therefore it experiences an upward force under the influence of gravity, which is downward in this case. Lower density rises due to buoyancy, carries along with it the heat, and ambient fluid comes in and gets heated up, and this cycle continues. If the surface temperature is Ts and the length scale is Lc, the characteristic Reynolds characteristic velocity for convection, that is determined by a balance between the buoyancy force and the inertial force density, and the buoyancy force density is given by G beta delta T Lc power half. Beta is the thermal expansion coefficient, delta T is the temperature difference. This temperature difference is varying with time in our problem, and therefore the characteristic velocity is also varying with time in our problem. The Reynolds number is Grashof number power half. Okay. Traditionally, it is the Grashof number that is used, not the Reynolds number. And the Grashof number is given by this. The other dimensionless group is the Prandtl number, which is nu by alpha. Okay. So, also Cp mu by k. Okay. So, the Nusselt number is a function of these two. In this case, the boundary layer thickness, the thickness over which there is a disturbance to the temperature field due to the presence of the sphere and consequently an upward velocity, that scales as the characteristic length times Grashof number power minus 1/4, which is why the Nusselt number scales as Grashof number power plus 1/4. Typically, the Nusselt number will be inverse of the diffusion length. Okay. So, the Nusselt number scales as Grashof number power plus 1/4 times a function of Prandtl number. And the diffusion time goes as Grashof number power minus half times Lc square. So, I had solved the problem of a heated sphere, temperature, initial temperature T naught in a fluid kept at temperature Tf far away. Okay. And we were trying to examine how that sphere would cool with respect to time. As it cools, the temperature dependence decreases and therefore, the buoyancy force decreases. Okay. That has to be incorporated in the calculation. Okay. So, we had written the energy balance equation for the sphere as the change in energy is equal to the surface area times the average flux. Average flux given by the Nusselt number correlation. The Nusselt number correlation now a function of Prandtl number times Grashof number power 1/4. Okay. The Nusselt number goes as gr power 1/4, boundary layer thickness goes as gr power minus 1/4. Okay. So, this was incorporated into the Nusselt number correlation. Okay. So, on the right side we have Ts minus Tf power 5/4. Recall then when we did both for low Peclet number and high Peclet number forced convection, the right side was also proportional to the temperature difference. That is why we got an exponential decrease. In this case, it goes as temperature to the 5/4 because there is a factor of temperature power 1/4 in the expression for the Nusselt number. And the approximation that we are making in this case is that this is the instantaneous Nusselt number. That is valid when the diffusion length scale is diffusion time scale is much smaller than the time scale for the variation of temperature. Okay. So, based upon that we had scaled the temperature. Okay. We had defined the scaled temperature as T star, okay, is equal to Ts minus Tf by T naught minus Tf. Ts is T naught at initial time, that means that T star is equal to 1 at initial time. And in the limit, in the long time limit, you would expect the sphere temperature to be equal to the fluid temperature Tf. So, T star has to go to 0. Okay. So, this is a measure of the departure of the sphere temperature from the fluid temperature. And we had got an expression for T star, right, that is that dt star by dt is equal to this one, where we had calculated the characteristic time. And then we had solved the problem. Okay, we had solved this problem and got expression for the characteristic temperature. Okay. This is equal to Ts minus Tf so in the limit as T becomes much larger than the characteristic time, this decreases 1 over T to the 4th power. Okay. In the case of diffusion as well as forced convection, it was decreasing as temperature exponentially with temperature. In this case, it goes as T power minus 4. Okay. And the condition is that T star the characteristic time Tc is much less than Grashof number power minus 1/4 into the characteristic length the whole square by alpha, okay, which is gr power minus half Lc square by alpha. Okay, that is the condition. Okay. That condition has to be satisfied for this to be valid. Because Grashof number is very large, this is likely to be satisfied in most practical cases. So, finally, before we complete this discussion of transport due to objects, I will solve the problem of spatial variation of temperature. Okay. And this is, for example, if you had an elongated object. Okay. Okay, so let me draw it a little longer. This is the length of the object. Okay. This heat exchangers, for example, very often you have a tube, okay, and you have what are called fins on this tube, okay, which are basically protruding radially outwards. Okay. And these are placed so that the heat transfer rate increases, because the conductivity in this is very large. So, the temperature, so if you have a metal tube with metal fins, the thermal conductivity is very large. So, virtually the temperature is the same everywhere. Okay. The temperature is the same everywhere, and by putting fins you have increased the area for heat transfer. So, the heat flux also increases. Okay. So, this is the kind of configuration that is observed. So, for example, typically you will have a tube on this side. Okay. This will be okay. This will be on the wall of a tube, for example, with tube temperature T equals T naught here, okay, and at the other side it will be TL, say, and you have, this will be in a fluid. So, if this is a heated object in a fluid, you will have natural convection taking place around this object. Okay, natural convection taking place around this object, resulting in enhanced heat transfer. Okay. So, there is going to be a variation along the length because there is conduction along the length and natural convection from the walls. Okay. So, let us assume that this had an area of cross section which I will call ACS, and this perimeter, the wetted perimeter, so to speak, of this. Okay. I have used the notation here, yeah, LW. Okay. LW is the perimeter. Okay. In this case, I can do a differential balance locally. Okay. I take a small thickness delta x. Okay. I take a small thickness delta x. Okay. So, if I expand it out, okay, this is the tube, and this is this is delta x. So, I do a differential balance for this particular length. Okay. There is heat coming in at the location x, heat leaving at the location x plus delta x, and heat that is going out due to natural convection on all of these surfaces. Okay. There is heat going out due to natural convection on all of these surfaces. I will not derive the details, I will just show you how the differential equation can be derived, which takes into account the effect of natural convection, and how we get the characteristic length scale in this particular case. So, what is the energy balance for this? Okay. The energy flux in the x direction times the cross sectional area at the location x. Okay. So, ACS is this cross sectional area, okay, minus the energy out times ACS at the location x plus delta x. Okay. The difference at steady state, the difference in energy coming in at x minus the difference in energy going out at x plus delta x has got to be equal to the total energy that has been convected by natural convection from the surfaces, okay, of this object, okay, by natural convection on the surfaces of the object. Okay. So, what is the energy leaving due to natural convection? Okay. This is equal to the average flux times the surface area. Surface area is the perimeter times delta x. Okay. Surface area is the perimeter times delta x. Okay. So, the energy leaving is QAV into LW into delta x. This has got to be equal to 0. Okay. That is the energy balance. Okay. So, I can divide throughout by the cross sectional area. Okay. I can divide throughout by the cross sectional area, okay, and divide throughout by delta x. Okay. So, if I divide throughout by the cross sectional area and delta x, I will get qx at x minus qx at x plus delta x by delta x minus QAV LW by ACS. This is equal to 0. Take the limit as delta x goes to 0. Qx at x minus Qx at x plus delta x by delta x is minus the derivative, okay, minus dqx by dx minus q average LW by ACS. Earlier we had said that for pipes and conduits in general, okay, the ratio ACS by the wetted perimeter is equal to the hydraulic radius, if you recall, okay, and the hydraulic radius was equal to the equivalent diameter by 4. 1/4 of the equivalent diameter for conduits, tubes, channels, etc., 1/6 for three-dimensional objects. Okay. So, we can substitute that in here, okay, and you will get minus dqx by dx minus QAV, okay, 4 by dE is equal to 0. Okay. And then here I substitute Fourier's law for heat conduction. That is because along the length of the object, heat is being transported by conduction. This is a metal fin. Within the object, conduction is the only mode of transport. Okay. So, substitute Fourier's law for heat conduction and you will get k d square t by dx square minus 4 q average by dE is equal to 0. Okay. And I can divide throughout by the thermal conductivity. Okay. Okay. Now, for this q average, okay, by k delta t by equivalent diameter. Okay. Length scale is the equivalent diameter in this case, okay, is equal to the Nusselt number. Okay, is equal to the Nusselt number. Okay. So, therefore, substitute that d square t by dx square minus 4 kf into t minus tf Nusselt number by dE square. This is equal to 0. Okay. And finally, we have to substitute the Nusselt number correlation as a function of Grashof number. Okay. Nusselt number is equal to a function of Prandtl number times Grashof number power 1 by 4, okay, is equal to a function of Prandtl number times rho square g beta into T minus Tf, okay, dE cubed by mu square. Okay. This is a function of Prandtl number. It's Grashof number power half times a function of Prandtl number. Okay. So I'll get d square t by dx square is equal to 4 kf into t minus by dE square, okay, into some function of Pr into rho square g beta t minus Tf dE cubed by mu f square. Let me put the subscript here to represent fluid properties. Okay, I'll put the subscript to represent fluid properties, whole power 1/4. So once again I can define a scale temperature, okay, that is useful in such cases because the temperature is varying. Okay. This temperature at the beginning of the fin is T naught, the fluid temperature is Tf. Okay. So therefore I can define the scale temperature as T star is equal to T minus Tf divided by T naught minus Tf, where T naught is the temperature at the temperature at the wall of the pipe if this is a fin. Okay. This would implies that T is equal to T star Tf Okay, so I can substitute that into this expression. Okay. Note that I have a factor of T star T minus Tf power 1/4 and T minus Tf. So I'll get T minus Tf power 5/4 here. Okay. Whole into T star power 5/4. Okay. Note that I have written here you have T minus Tf power 5/4. I have written that as T naught minus Tf power 5/4 times T star power 5/4. Okay. And you can simplify this divided by characteristic length square, okay, just from dimensional analysis. The left side has 1 over length square dimension, the right side also should have a dimension of 1 over length square, where this characteristic length will be equal to root of okay. I missed out this factor of K here. Okay, this is a solid conductivity, so there should be a Ks, Ks. Okay, kindly note that. Okay. Because I have used the relation Kf into dt by dx here for the flux. Okay, and there is this factor of Kf here. Sorry, K. Minus Ks into dt by dx. Okay. So, that factor of Ks comes down. Okay. So, I have to divide throughout by Ks everywhere. Okay. This whole into dE power 5 by 8 mu power 1 by 4 by rho square, rho f square g beta delta t. This whole thing to the 1/8 power. This is the characteristic length and this is the equation. Okay. This is the equation for the temperature and this is the characteristic length. Okay. So, now we have a characteristic length for the variation of temperature along this. Okay. So, what would you expect? So, you can evaluate what the value of this is. Okay. And of course, you can solve this equation. Okay. You can get a partial solution analytically, but you have to solve it further numerically. Okay. Okay. You can do one step of integration in this equation, but more than that you have to do it numerically. Okay. But we have a first order differential equation, ordinary differential equation, which we can solve. Sorry, a second order ordinary differential equation in x that we can solve. So, what is the use of this? Okay. So, we have actually evaluated an expression for this characteristic length. Okay. How do we actually use this? The characteristic length is the length over which the temperature decreases because of natural convection. Okay. So, if I have a fin of length L, say, okay, if L is much larger than the characteristic length, that means that the temperature decreases. Okay, if I plot the temperature as a function of x, okay, decreases over length scale that is much smaller. Sorry, it can't go below 0. The temperature decreases over a length scale that is small compared to the characteristic length. So, you get no advantage over having a long fin. Okay, you get no advantage over having a long fin. Okay. On the other hand, if you have L much smaller than LC, right, then the temperature along the surface, okay, because LC is the characteristic length, the temperature does not decrease very much, okay, over the entire length of the fin. Okay, x is equal to L. Okay. So, there is not that much variation in the temperature along the length. Okay. So, therefore, there is not that much conduction. So, you would like to have a situation where L is comparable to LC, so that there is a significant decrease in temperature by the time you reach the end of the fin. At the same time, you do not have regions far from the pipe wall where the temperature is equal to the fluid temperature. In that case, there is no advantage to having that length, because temperature is already equalized and therefore, there is not much conduction taking place there. Okay. So, there is virtually no conduction taking place. So, there is no advantage to having a fin length which is much larger than LC. If it is much smaller than LC, then you do not get sufficient surface area, because the temperature is the same as the temperature of the pipe wall. the temperature has not decreased very much as you go along the length. Okay. So, LC is the characteristic length over which the temperature varies, and the length of this fin has to be made comparable to LC, so that you get maximum advantage of significantly high conduction, but not the disadvantage. There is a large region in the fin which is at the same temperature as the fluid temperature. So, no conduction takes place there. And the other criterion is, of course, LC has to be much greater than the characteristic diffusion length, that is GR power minus 1 by 4 times dE, for the steady state approximation to be valid. Okay. So, you have to verify that this length is much larger, okay, so that you can assume a steady state at each local position in the fin. Okay. Note that there is actually a temperature variation. Okay. As you go downstream here, the temperature actually decreases. Okay. Okay, if I plot the temperature as a function of distance along the length of the fin, the temperature decreases from one side to the other. Okay. So, this is not actually a constant temperature which is assumed when the correlation is derived. Okay. For elongated objects, you assume that the temperature is a constant when you derive the correlation. In this case, the temperature is not a constant. However, we can consider it a constant if the characteristic length for the decrease in temperature is much smaller than the diffusion length, which is GR power minus 1/4 times the equivalent diameter. So, this is an example where a constant temperature correlation has been used to calculate the varying temperature along the length of a fin. That is valid when the length is much larger than the diffusion length, which is GR power minus 1/4 times dE, and in that case you can get an expression for the time variation of the temperature by a differential balance locally at each location on the fin in order to find out what is the variation temperature along the fin. So, this completes our discussion of natural convection. I will continue this with another problem in the next lecture, that is, how do you use correlations for flow through a packed column. As you recall, we looked at the Nusselt number correlations as well as the friction factor correlations for the flow through a packed column. I will examine how we can use these correlations, which are based upon steady state, to calculate the variation in temperature with position in a packed column, where the temperature is a function of the coordinate along the length of the packed column. This I will continue in the next lecture. I will see you then.